Okay. We want to try to finish the whole ADT of the binary search tree that we started on Tuesday. You're going to have a couple of questions in the assignment 2 about binary search tree. And of course, it is covered in the midterm. So we'll try our best to cover everything today. And then anything left, I'll definitely record for you the tutorial for the binary search tree. I'll record it during the reading week, so you can take a look at it. Now, if you remember, we talked about the MAP ADT. Who can remind me very quickly what's the difference between the MAP ADT and the priority queue ADT that we talked about previously? Yes.
On the map, we have the key and the value, but we don't have the other.
Very good. So the priority queue, we had a key and the value, right? Like the element. The key represented what in the priority queue? It represented the priority of this element. And we usually always want to access this data structure that we have based on its priority. That means I don't need, it's not my problem to go and be able to access any element there. No, I need to only access the one with the highest priority. But we said, what if we want to have a different application? We want to store your information in my data store, okay? The student's information. In this case, I still need a key, which is your student number. It's a unique key. You remember, it's a unique key. But I don't want to access based on priority. So I'll need a different way where I can access any student I want. Okay, so that's where the MAPS ADT comes in play. Now we said we can actually implement this using unordered sequence or ordered sequence as usually, and we're going to say we're going to see that we can also implement it using search trees. And today we're going to cover binary search tree, and the next lecture we're going to cover AVL and 2-4 trees, and then also the hash table and the lectures after that. Now, something very important, guys. We said in the map is different than the priority queue. In the priority queue, you can have 2 elements with the same priority, correct? Let's say in the emergency room, 2 people broke their leg, same priority. But in the map ADT, it has to be a unique key. Why? Again, the same example, student number, it cannot be the same thing. Phone number, it cannot be the same thing. Let's start talking about implementing them. As usual, how do I assess my ADTs? How do I assess the ADTs? Yes.
Is it usually on if it's usually if it's array or?
Yeah, so technically I want to assess them based on the efficiency, which we learned we're going to choose the algorithm, and then we're going to try to assess this algorithm. What is the big O of this algorithm? Which one is better? And then I'll choose the best algorithm. So as usual, we're going to start with the sequence, with a linear type. So I want to implement the maps using, the first thing to talk about unordered sequence. Now, this unordered sequence can be implemented using an array or a linked list. We already covered this. If I want to do get, remove, and put in this unordered sequence, what would be my big O? What would be my algorithm analysis? Fida. O of 1. Riley. Same answer, different answer. It's okay, we'll just leave. So O of 1, O of n. So these are the 2 answers I am assuming. Okay, so who wants to say more? Y, O of 1? Yes.
So we can just like here and assign the view. So
Riley, Y of n.
You have to loop through things to get things. So if you wanted to get a specific instance in your list, you still have to loop through, right?
Yes, why? Because if I want to get a specific key, I want to search for it. I want to traverse. So if I want to traverse, it has to be O of n. Now, what about remove? Again, the same thing. I want to remove a key, but first I need to know if this key is inside this or not. Now, what about put?
Or I guess it doesn't matter, just add it to the head, over one.
So O of 1. Any O of 1 also for put? You said O of 1 for everything, but O of 1 for put? Anyone else? Yes. O of n for put, why? But this is unordered. So I can just, Riley, for example, said I can just throw it here at the end, so O of 1. Because it's unordered. I don't have to put it in order.
I don't know, maybe there's an exception if the key is already.
To go through it. But why we have to go through it? No, no. So usually we have access to in front and in the back. So if I'm putting it at the end, I can do O of 1. Why? Because this is a, let's say it's an array based, for example. Array based, what do I have always? Index of 0, which is the first one, right? And then I always have index of the last one, which is n minus 1. If I know what is my size, then n minus 1 is my index for the last one. So O of 1 for array based. For linked list based, also I know the head and the tail. Very good. Very good. So O of n for get, O of n for remove is very clear. Now the put, we said this has to be a unique key. So if I want to put a key, I have to check if this key exists first. So I have to search actually first. If it doesn't exist, I can do the O of 1.
Search, so it's still n, right?
Yes, you said O of 1. That's what I'm saying. Yeah. So O of 1 for just inserting it, but before I insert it, O of n to search. So all of these is going to take me O of n. And we said the insert part is O of 1, but I have to search, which is going to take me O of. Yes, Ant.
Base implementation insert is also O of n, because if we exceed the limit of our array, like if it's dynamic, are we assuming that it's a static?
So this is, we're saying this is for both linked list and array.
Okay.
Why? Because in the array, the same thing, you have to search for the key first. And for the linked list, you have to search for the key also. In linked list, we don't even have index anyway, so we have to search. We have to traverse for a linked list. But for a linked list, usually when we used to remove or something, we used to be O of 1 because we used to if I know where I am, it's going to be O of 1. But again, both of them is going to be O of n. That's why we just left it as unordered sequence. So both them. Now, some of you will tell me, okay, let's solve this issue by doing ordered sequence. Okay, let's try. You don't like the idea. Why do you think it's not going to be solved? But what would be the problem? Put, yeah. What would be the problem in this case? Exactly. So now it is true if I do ordered. Okay, ordered, maybe it's easier for me. But if I want to insert or remove, what will happen if it's an array? I'll have to, let's say I removed 14, I'll have to switch everything there if it's an array based. So I'm still doing O of n. And they're removing the same thing. Now, the only thing that can be improved with the searching, if I'm using an array based, because if I'm using a linked list, the same thing. Linked list, I don't have a index. So I have, whenever I want to search, it's going to be always O of n. But with an array based, what's your name again? Amin? Amin said, we can do something a bit better with an array based. He mentioned binary search. Why binary search can be done only with an array based, not with a linked list. Binary search, of course, we covered it in previous courses. James.
Is that way you're able to invest it, as you see for the heaps, it's 2x plus
Yes, it has nothing to do with heaps, but because in the binary search, you need to always do index. Why? What is the concept of binary search? You need to find the middle and then decide. We're going to see it now. So if to be able to find the middle without traversing, I need the index. And the array base is the only one that will allow me to have index. So let's take a look here. So we said inserting, removing, I cannot improve it with the sequence, but in the ordered array, I can improve the search. No problem. Now, before we move, we said maps are one of the most important ADTs, even maybe more important than the priority queue in general, even though if you have a specific problem, of course, you're going to go with the specific ADT. Why? Because searching is maybe one of the most common tasks that we all do, right? And why it's important to have more efficient search these days in 2024. Why? Because of course, James.
So with larger sets of data.
Exactly.
The impact is more.
Exactly. 2024 now, you know, you have humongous amount of data. So the more data that you have, that means it's going to take you more to search. If I want to search this 140 seats, it's not a big deal. If I want to search 1 million seats, 1 billion seats, and you know the story of Google, the name of Google, what does it represent? So Google is what? It was a mistake. I think they made a mistake here. It's like 1 and I don't know how many zeros next to it. Yes.
10 to the power of 100.
10 to the power of 100. And the idea of the name of Google when they did the search engine is that they have what? Huge amount of data. And then you need to search for it. So their search engine is very good and all these things. Okay. So because we have big amount of data, as we said, it's very important for us to make our search very efficient. So that's the first step. Now, let's just remind ourselves about binary search. So far, are we talking about a tree? Did we mention any trees? No. Because the MAP ADT can be implemented with an ordered or unordered sequence. We didn't reach the tree part. So when I say binary search, I'm talking about binary search, not binary search tree. Okay, binary search, which you've learned before. I need an array. Why? Because I need the index of the last one and the first one, which represent, let's say, low and high. So in this case, if my array is n equal 13, what would be my h? 13 minus 1, correct? It's going to be 12, and then my low. So these are, I'm creating them. Why? Because I want to build my algorithm, my pseudocode. I need them. Then how can I find in the binary search tree? What do we do? High minus low over 2, correct? And we do the div one, just in case we have, let's say, for example, 6 point something, we only take the 6. What will happen next? I want to check if 7 inside this array. The first thing, I'm going to compare it with my middle. If it's not, I'll check, is it less or greater? In this case, it's less, so I scrap all of this. So now I'm only need to loop through, not loop, like need to search through n over 2. Let's say I have 1 million data inputs. Now I only need to go through 500,000. So I saved half of them. Each iteration, I'm going to save half. So that's the power of binary search. But it only works with what? Arrays and sorted. They have to be sorted. Okay. So let's take an example here. So we want to find 7. We went again and we're calculating H and L again. We didn't find it. 7 is greater than 3 again, and then I'll find it here. Very good. Now, what is the pseudocode for binary search? Again, we're not talking anything about trees, just in general. That's why we need the high and the low, because you're going to always base everything you do on the high and low. These are two keys. If the low key now is greater than the high, that means I didn't find it. The search is unsuccessful. If the mid, if key equal key mid, then return key. If not, then start comparing them. And then what is this here? It's a recursive call. Now the fun part, because someone is telling me, okay, I don't trust you. You're saying binary search is log of n. Prove it for me. So we're going to just go very quickly for a math proof. Okay, so look here. First, I'm starting with n. So follow the pen because these are overwhelming numbers. There's too many numbers. So just follow the pen here. So n. After the first iteration, I got rid of half of them. So I'm n over 2, correct? Second iteration, n over 4, and then I'm going like this. What can we notice? I'm only looking at this, the search range. I'll notice that this number here is always 2 to the power of the iteration. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, right? So this is always matching the iteration. So can I conclude a general rule here? Yes, I can say that for I number, I will have n over 2 to the power of I. Okay, so I can conclude this. Now, let's take an example. If I take 32 as an example, so I'm starting with 32, correct? How many comparisons, so how many time I need to go to divide to reach my number or unsuccessful? So let's try it. I'm 32. I divided by 2, I'm 16. Then 8, then 4, then 2, then 1. So it took me 5 comparisons. Let's say I'm 16. I started with 16. It's going to take me 4 comparisons. And you can continue like that. So what I can conclude here, 32 is 2 to the power of 5, 2 to the power of 4, 2 to the power of 3. So I can say it will take me log of 2 to the power of I to have I comparisons. Okay, so I concluded another rule here. How can I match these two? I can say here what n equal to 2 to the power of I. I just brought this here. And then I'll replace this 2 with n. So I can say that I is equal to log of n. So if I have I comparisons, that means I have log of n comparisons. Okay, so that's the math behind it. Again, at home, take a look at it slowly and check it. So now I proved for you mathematically that it's going to take us O of log n for the binary search. Someone is going to tell me, okay, we solved the searching issue with the ordered sequence, but I still have a problem with what? Inserting and removing. It's still O of n. Who can reply to this statement? How can we improve? How can we fix this? Based on what we've learned. Let's see more people. Based on what we've learned so far. Because now at this point, you know how to tackle the issue, correct? And then you know how to think. I don't have to call Anthony and Zach each time. Let me help you. So what do we usually do all the time? Do we know what's the problem? We know what's the problem now, correct? Okay. Do I know what ADT I need to use? We said, yes, I know it's a MAP ADT. So what's missing now? The implementation of this ADT, right? The algorithm. We said the first algorithm that I tried was the unordered sequence. It didn't work for me. Then I tried another algorithm, ordered sequence. It only solved what? The search. So what should I do as a computer science? What should I give up? Okay, what should I do? Exactly, not another ADT, another algorithm. Let me try another algorithm. Okay, very good step. What other algorithms we can try? Because we have a bag of data structure, we said. James.
Linked list average, but linked average, I mean linked implementation.
Linked list, we already tried it, it didn't work also.
I know what I mean is that we use nodes, so that way we go left or right.
Yeah, but think about it. It's not linked list, it's what? Because linked list, like for example, you mentioned the heap, right? A tree, exactly. Because a heap or a tree can be implemented array or linked list. No, we want the more general data structure. James suggested here, we still have in the bag binary tree that we already implemented maybe a couple of lectures ago. So what did we use there from the binary tree? Remind me. Let me see. What did we use from the binary tree? What did we solve? We used it for the priority queue. So what did we use? Complete binary tree. Okay. Okay. Riley say, you know what? I'm going to use a complete binary tree. Maybe it will help. Let's take a look. So this is an example of a complete binary tree. I have 5, 10, I have 20, 1, 17, and then, for example, here I have 30. Okay, this is complete binary tree, correct? If I'm implementing this complete binary tree with an array, so how can I put it? So this is 5, 10, 20, 1, 17, 30. What's the problem? Can I use it?
Not sorted.
It's not sorted, so complete binary tree is not going to work. But we're very close, because when you said complete binary tree, because you're thinking, okay, complete binary tree, it gives me the height of log of n. So it's going to save me when I want to insert and remove. So I want the aim to be log of n. But maybe I can come up with something similar to a complete binary tree, but it's more ordered, right? So that's where that search trees comes that we didn't explain yet. We're going to start from today. One of them is binary search tree. Very similar idea. I want a tree, but I want it to be ordered. So how can I improve my tree to be ordered? We're going to see today. You have a question or? Okay. So this is what I was talking about today now with you. So this is the summary of the bigger picture. So we said we solved the issue of searching by log of n, but we still have a problem when it comes to insert and remove. So we're going to try a new algorithm search tree. So what is a binary search tree, guys? It's everything on the left of the parent of the node is going to be less. So actually, you can just put like this. Everything here is going to be less than 6. Everything here is going to be greater than 6. Again, don't make the same mistake that we did in the heaps on the min and the max. We don't only look at the root. So this even here, everything here is going to be less, everything here is going to be greater. Good? So we will have, again, 2, we'll have a key. This is 44 represents the key, and then also it will have an element. Then here we can have a dummy leaves usually are for what? It's just for me to stop when I'm searching. They'll act like an external leaves. Now, a question. This is a binary search tree, correct? Because everything here, if you look, all of these are less than 10, and all of these here are greater than 10. So this is a binary search tree. Now, if I ask you, how can we traverse the tree so that we visit the element in an increasing key order? Let me see. So I want you to think a bit more. Yes?
You can do in-order searching.
Very good. So the first thing is I want to check, what did I learn? We learned pre-order, post-order, in order. Okay, why did we go to the in order? Pre-order is visit, left, right. So the root will always have the first number, correct? So 10. If I start with 10, that's not sorted. The post-order is left, right, visit. Also is not going to work. So the solution is the in order, of course, which is left, visit, right, or left, center, right. I'm here, I go left, I go left, I'm visiting 1 first. Then I'll visit 3. Then I'm here. Left, visit right. So I'll go to the left. That's 5. And we continue doing this. So it's in order for increasing order. Increasing. Now, if I want to do decreasing order, what will happen? I cannot use in order, but I can write my own algorithm to start. Instead of left, I'll start from the right, for example, and then recursively do the same idea of in order. Very good. So this is from the book, The Binary Search Tree. Now, please focus on this. Again, I want you to always remember the difference between the ADT and the implementation. What are the operations here? We have all of these operations. We have 1, 2, 3, 4, 5, 6 operations. What are the operations that are referring to the MAP ADT? The MAP ADT has operations. The MAP ADT. Melanie. Get, put, and remove. Why not 3 search, 3 insert, 3 delete?
We're not using the tree.
Because in a MAP ADT, I can either use sequence or I can use a tree. Correct? So that means now in this case here, I want to use a tree. So I'm going to have 3 search to act like get, 3 insert to act like put, 3 delete to act like remove. But if I'm building my ADT using a ordered sequence, for example, I'll replace these with the ordered sequence operations. But the interface will always stay get, put, remove. The interface of the MAP ADT will always be the same. Because here, this is my ADT, which is a map. We said inside it, I'll have what? For example, data structures, right? Here, the interface will be get, put, and then remove. If I'm one of the implementation of this ADT is through binary search tree, which will have what? 3 search inside it, 3 insert, 3. Another implementation can be with the order sequence, which will use what? Something else. Clear? The difference? Okay, very good. So now, what will happen if I say I want to get 4? We said we cannot just get 4 right away, even if it's array-based. I need to search for the key first. So I'm going to search. So I'm here, I'm 4. Is 4 less or greater than 6? Less. So I'll go here. Is it less or greater than 2? Greater. I'll go here. I found 4. Yes.
So to maintain the log n speed.
We didn't reach this. We're not going to be able to maintain it now. We're going to talk about it. Now we're just the idea of a binary search tree.
You still want it left filled. You can't have an incomplete tree. You don't want it incomplete.
No. I don't care about complete binary tree here. That's a different concept. It's called binary search tree. Now, if I'm going to come up with examples and we're going to explain it very well. But very good questions. So the idea here, guys, each time I want to search or insert or remove, I'm going to always start from the root, always from the root. And then I'll compare. 4 is less than my root. Yes, I'll go here. And then I'll continue. Okay, so that's first thing. Let's do an example. I want to call the tree search to search for 76. I will always start from where? The root. Is 76 greater than 44 or less? Greater. So I'm going to go to here. Now, again, is 76 greater or less? It's going to be less. We'll go like this. Again, I'll go to the right. Then now I went to the left. I found it. It's a successful search. Okay, very good. Again, we're still not talking at all about the cost. Just understand the idea of a binary search tree. How can I build one? Another search example. This will be unsuccessful, for example. How can I know it's going to be unsuccessful? I'm going to reach an empty node, an external node. If I reach an external node, I'll be able to stop. Why we're visualizing these? Because the next step will be building your pseudocode and then transforming into Java. So now you can do if external node, blah, 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 unsuccessful search, for example. You know, like these things are important for you. And then we reach here, this is unsuccessful. Now we're going to start talking about the cost. Yes, right.
Suppose I had a binary tree and I started with my root was 44, and I added 45,
Okay, so let's
46, and then I had a straight line all the way down. Don't you have to look at it? Okay.
So we're going to reach this. We're just building the floor for it, okay? Preparing the floor. Now we got the idea of a binary search tree. Binary search tree, the only thing it's going to fix for me is going to allow me to have a binary tree while ordered. That's the only thing guaranteed for me, which is that everything on the left is less than the root, everything on the right is greater. So I solved the problem of ordered versus unordered. Now I want to talk about the cost. Why? Because all of this, as Riley said, is useless if I don't get a good cost. Correct? Okay. What do you mean by cost? Time complexity of the worst case. Correct? Okay, very good. So if I have something like this, and this is a binary search tree, so I have, let's say, 7, I have 10, I have 20, 30, and then 33. Okay, so are these unordered? They are unordered. But what is the height here? This is something very important for the quiz, the online quiz, for the midterm, for the final. How do we do the height? We always start with 0, not 1, guys, 0. So here, level 0, 1, 2, 3, 4. So my height is 4, not 5. Okay, it's important for you when you're writing your answer in the quiz or the midterm or the final. So this is called the worst tree. So that's my worst scenario for a tree that's going to be skewed. Now, what is a better or the best tree is something like this. Okay, we saw something which is a perfect binary tree. We saw a complete binary tree. All of these are considered best tree, but they don't have to be complete or perfect. Even this one is still a best tree because it's balanced. Very good. Now, what would be the cost of search for the worst tree? Let's take what is my worst case, the big O, the worst case of this. Who can tell me? N. Why? It's skewed like that. I have to, that's my worst case. For example, the last one. So O of N, correct? So what would be my average case of the worst tree? So it's like, for example, big theta. Okay, so I have a worst tree, and I want to get the average. What do you mean by the average? Yes, James.
I would also be average.
Yeah, but we want to understand the steps. So what do you mean by average?
That being said, you'll probably try to go for somewhere in the middle.
Very good. That means, I don't know, maybe I'll get something in the middle and I stop. That's successful search, right? How do I usually, we've done this before, how do I usually calculate this? We're going to say, yes, Joel.
Upper bound and lower bound?
No, we're not going to go mathematical. We're just talking from here, from example-wise. So what are the average? How do you usually, if I have an array like this, if I want to search for something, what would be the average case? Maybe you find it here, maybe here, maybe here, maybe here, maybe, and like you have to calculate the probability of everything. How do we do that? We're going to say, okay, if it's here, it will take me off 1. If it's here, 2. If it's here, 3. And then I'm going to say, okay, it's going to take me 1 plus 2 plus 3 plus divided by what? The number, which is the average, correct? Basic math. Now, if I say 1 plus 2 plus 3 plus n, what did we learn? This Gaussian summation is what? N over n plus 1, sorry. It's n times n plus 1 over 2, correct? So it's going to take me off n squared. You don't agree, David, right?
The average divided by n, no?
Exactly. We still didn't do the average. We need to divide by n. If I divide by n now, this n is going to go. I'll have n plus 1 over 2. This is big O of what? Of n, like James said. Big O of n. Yes, I mean,
That's the answer where the worst case is already.
exactly. Very good. But here I do these, that's your first time attending, right? So I try to trick the students so they can pay attention. That's why we do these things. Okay, so it's of what? Of n. Now, unsuccessful search. Even the average unsuccessful search, not the worst case. What would be?
There's no average on this. We should have to go through everything.
The average case of unsuccessful. Riley.
You'd have to look through everything and search for everything, so it'd still be over.
Exactly. Unsuccessful that I'm not going to find it anywhere. I have to reach the end anyway. So it's going to be all the time O of n. Average or best or worst. O of n. Now let's take a look at the best tree. The best tree, guys, is what? Can be a perfect tree, complete binary tree, or a balanced tree. All of them, they are best tree. What is the common thing is that we're going to always end up with log of n. Okay, we already proved it. We're not going to go to the proof for this. When I have a perfect, complete, or a well-balanced tree, I'll end up with I log of n. That means my worst here, like the longest I can go, is log of n. That's my height. Correct? Very good. So what did we say here? The worst case of the best possible tree is O of log n. But let's give some example. That's the worst case of the best possible. What about the average best tree? The average is harder. The worst case, I can just say, okay, log of n. It's the height. It's the last one. The average, I need to do something, the same exact thing that I did. It may be the first node, maybe the second, maybe the third. So I need to add them. But in this case, what am I adding? The log of n instead, not the n. So I'm going to end up with n log n over n. We proved why is this n log n from previous lectures. Also, it will stay log of n. So for the best tree, it will still, the average be log of n. Unsuccessful, log of n. Again, unsuccessful, I'll reach the end, it's O of n. So what can I conclude here?
That's good.
I gave best tree, I gave worst tree. This is super, super important, guys. This is what super important. Because that's the mistake that I'm sure, even now I'm saying super important, it's recorded, you're going to watch it. I'm sure that 40% to 50% they are going to answer wrong in the midterm. What is the big O of a binary search tree? Raise your hand. What is the big O of a binary search tree? So what is the worst case scenario for a binary search tree? As we said, it's very important. So please, everyone, think about it. Take a bit of time. I have 1, 2, 3, 4. We'll go with you. O of n. Okay. We have one answer so far. We have Joel also. Who else? Think about it. What is the big O of a binary search tree? Okay. And we have n. We have n log n. Ahmed. Log n. So we have n, log n, n log n. Very good. That means we're thinking. Anthony.
Are we allowed to ask you like what the current state of the tree is, or is it just a tree in general?
This is a part of the answer. So you're on the right path. I'm dead. You cannot ask me anything. There is a voice of revelation now talking with you. You cannot ask me anything. So continue with this thought.
So if it's dead, that means we have to go ultimately to the worst case scenario. Because
Or we can have something reasonable and say it depends on what? On the tree. That means if it depends on the tree, technically it's depending on what? No. So what is depending on this? Forget the word worst or best tree. What is this? Why is this worst tree? Why? Because H is equal 4. And this is H equal to what? 0, 1, 2, 3. So what are we depending this on? On H. So can I say it's O of H? This will give you a general answer for binary search tree. You cannot say it's big O of log n. You cannot say big O of n. It's big O of H. So whatever H is going to work. If it's n, if it's like this, it's going to be O of n. If it's like this, it's going to be O of log n. So that's what I want you to always remember. Big O of binary search tree is the big O of H. Okay, it depends on the height. Okay, guys, remember this. Why? Because we're going to say if the binary search tree is the best tree, we're going to end up with O of log n. Or if it's worst tree, we're going to end up with O of n. That's why you're not going to be satisfied with the BST, and we're going to learn about the AVL. What is the AVL? So this is a balanced tree, correct? And this is a skewed tree. What's the problem here? Can I guarantee for this tree to always be balanced? No. So AVL is called a self-balanced tree. So I'm guaranteed 100% to whatever I add, I delete from the tree, it's going to self-balance itself. I'm going to always end up with height equal log of n. That's when I can say the big O of an AVL tree is log of n. Okay, so binary search tree is not enough for me to have a general cost for it. Very good. So this is a summary for you guys. The worst case search for an arbitrary binary search tree is going to be O of n, as many of you said. Yes.
I'm just a bit confused about the skewed tree.
Mm.
You learned that it's a binary tree, right?
Mm.
You learned that the height of the binary tree is always log of n. So why do we?
No, we didn't learn this. We learned the height of a complete binary tree is always log of n, not a binary tree. Okay, so that's why now with the quiz, with the online quiz, you'll have to go and, because you're going to get some questions like this, you're going to have to go to the lecture and check these answers. So it's going to you're going to practice more. Okay, so again, so as we said, we can say O of n if you know that this is an arbitrary binary search tree, that I don't know what it is. Okay, worst case O of n. But if you want to give a solid exact answer, it's O of H, depends on the H. But you can say worst case O of n. Very good. So let's just go through this a bit. So now from an algorithmic perspective, from a pseudocode perspective, how can we actually write this? If I want to insert something, I need to call, because what will happen, I want to insert, I'm going to reach to the leaf. I'll find it's a leaf. So I need to call something. I'm basing this on a binary tree. In the binary tree, we learned that we have this method called expand external. Do I need to write a method from scratch? I can just call this expand external. It means that I reached here. This is an external node, correct? So I'm going to call this expand external, which will do this. What does this do if you remember from previous slide? What does the expand external? It will add the number. It will create two what? Leaves, new one and new two. And then it will increase the what? The, say it again. The link. It will increase size, exactly. So it will be size plus 2. Very good. Very good, guys. So this is previous slides. We already explained these. Now, insertion in case 2, what will happen? It's not a, we will find it. So if I find this key, what will happen? I'll just replace it. I will update the key, the value of it. Very good. So again, this is the algorithm. and it's based on the expand external. What else? Okay, now we're going to practice these together, because I'm sure many of you are still confused about the difference between a complete binary tree and binary search tree. Let me take this example, guys. Okay, from 1 till 9. I'll do this example with you. So I have this. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Who wants to do this based on complete binary tree? Yes. Complete binary. No. Complete binary tree. We start with 1, so that's 1. Okay, what's next? 2 goes to the left or the right? Left. Okay, what else? 3, where? Right of 2? Exactly. Okay, why you're doing this? Because the complete binary tree is left filled. So that means 4 is here, 5 is here, 6, 7, 8, and then 9. Okay, that's how I fill a complete binary tree. Okay, I do it like this, left fill. Now I want to do it. This is complete binary tree. Now I want to do binary search tree. How do I fill them? I'm doing 1. Who wants to do the 2? Yes. On the right. Why not on the left? Exactly, because binary search tree has nothing to do with complete binary tree. It's not left filled. It's based on the greater or less. So 2 is greater than 1, I put it here. What about the 3? You want to continue? 3 on the right also, right? Okay. Now pay attention to this thing. In this case, it's okay to look at the 2. But in the binary search tree, you're always going back to the root. This is very important, guys. So I have 1, 2, 3. Now I want to add 4. I don't look here if 4 is greater or less. In this case, it's going to be fine. But I need to always start from the root again. Is 4 greater than 1? Yes. Is it greater than 2? Yes. Is it greater than 3? Yes. I'm going to go like this. Okay? Then 5, then 6, then 7, 8. So in this case here, if these numbers are ordered, what's going to happen? I'm going to have a skewed tree. Please do the number 4 in front of you. Number A. Number 8. Do the first thing. Binary search tree for the first one. 5, 8, 3, 7. Do it in front of you. It's better to practice here so you don't spend hours at home trying to figure out the quiz. So please practice here with me and ask me questions. So we want to insert 5, 8, 3. We're going to start with 5 first, and then we're going to go continue. Again, binary search tree, not a complete binary tree. Done? Sorry? Okay. You're done, guys? Who still needs more time? Okay. Who wants to volunteer to do it? Let's see new people. Who wants to volunteer? Yes, please. So let's start together. We're going to start with 5. What's next?
So on the right,
Guys, please pay attention to this. On the what?
8 will be on the right.
Why did we go with 8 on the right? We compared it with 5. It's greater. We went on the right. Okay, very good.
And then 3 will be on the left.
The left of what? 5 or 8? 5. Okay, guys, pay attention here. Why did we put 3 on the left of the 5, not the 8? Because it's the rule that we have to always go to the root again. So this is the common mistake that everyone's doing. Usually, people may put the 3 here because they stopped at 8, they will continue from here. It's not going to work. It's not going to be a binary search tree anymore. 3, again, I'm comparing it with the root. It's less than the root 3. Thank you so much. Who wants to continue? 7? Yes. So I'm here. 7 is greater than 5. I'm here. It's less than 8. So I'm going to put it here. Very good. And then 1. Yes.
Left of 3.
So left to the left of 5, left of 3, and that's 1. Very good. And then 9, guys. So 5, 8, 9 is here. And then 2. Who's still confused about it? He wants to do it. If no one is confused, I'll go faster. Okay, very good. So that means we're going to have 2. 2 is less than 5, less than 3, and then greater than 1. That's 2. Less than 5, greater than 3. That's 4. And then greater than 6, less than 8, less than 7. What is the height of this? Who can tell me what is the height? Raise your hand. Yes?
3.
So we start 0, 1, 2, 3. My height here is equal to 3. Good? Very good. The C, I'll leave it for you to do it. But now, guys, if you do the complete binary tree of A, the height will be very good, but it's not going to be ordered for the complete binary tree. Now, what do we notice, guys? When would the best tree, when do you think the trees work the best? When? Because we tried A and B. What's the difference between them? Why B was very bad, A was good? Why, guys? Criticalthinking.com. Yes?
But B is sorted and A is not, and A is sort of started in the middle, I'll say.
Very good. We're going to cover this in the AVL tree, but technically you notice that when the input, when I'm giving you a sorted input, it's going to have a problem. You're going to have a problem doing the binary search algorithm. So you need a randomized input, and this is not very good. We're going to talk about this issue in the AVL. Now the delete thing, okay, I'm not going to spend too much time, but it's very important for you to know something. If I'm deleting 4, it's easy. I'll just put 5. Why? Because it has an empty left. So that's the only one that can go up. Correct? Very good. But what would be the problem, guys? And algorithm-wise, it's going to call the remove above external. We talked about it before. This is slides from previous lecture.
Yeah, put it as the root.
Now look at this. The same thing will happen. Because I have something empty here, I will just take this and put it here. That's fine. When would I have a problem? When I want to remove something like 3 and it has 2 children. Okay, which one should go instead of 3? 2 or 8? No, so technically here, no, we're not going to compare to the root at this space, at this stage now. So we need to have a proper formal way for the algorithm to understand how it's going to tackle this. Because you're looking at this, it's easy for you to decide. But how can I do a generalized way? That's why we're going to have it in order. So if I know the in order of this, what is the in order of this one? It's 1, 2, 3, 5, 6, 8, 9. If I'm deleting 3, I can always replace it with 2 or with 5, and it's going to stay the same order till I'm saved. Now, what would be the problem in this case? So not the problem, the better thing to do. If you have 2 options, 2 or 5, which one you should use? Logically, now we're talking. Why 2? If you know the indexes, it's not going to matter. For example. Riley.
Who has less like children? Or easier that way.
Okay, think about why we're even applying what is the main problem of binary search tree. It's O of H. That means what is my main problem?
That 6 is not in the correct place.
It isn't going to be in the correct place.
It would be.
Because if you're doing in order, it's still going to work. So let's say I put 5 here, 1, 2, 5, 6, 8, 9. It will matter. Again, look at the main problem. Joel,
The height of the tree would be shorter now.
exactly. We said the problem is O of H. I want to keep H as short as possible. If I put 2 here, my height will still be 0, 1, 2, 3, 4, correct? But if I put 5, what will be my height? 3. So I got a shorter tree. So usually I always choose the one with the longest part. That's the best. But this is going to be solved by itself in the AVL. In the AVL, we're going to impose this rule. Whenever you want to delete something, always choose the longer side so you can have a balanced tree. Yes.
How do you know which side of the model is the best?
We're going to see it in the AVL. Okay, because in the AVL you'll have something like, you know, the I, you know, in the heap when we had I to I to I plus, we're going to have something that's going to be very easy for you to figure out the index. So the idea here again, guys, this is very important. If I want to delete this, I have 2 options in the in order, the one before it or the after it. Now let's say you don't have these keys, because in the keys it's very easy. You don't even need the in order. You're going to say, okay, 2 is less than 5 and 5 is greater than 6, so I'm going to choose one of them. But what if this tree is represented by the elements, not by the keys? So I'll have here, for example, random stuff. I have A, I have Z, I have C. In this case, the in order, or another thing, you're going to choose the rightmost node on your left or the leftmost node on your right.
Okay.
Okay, think about it a bit. Let's move faster here. So again, practice, practice, practice. It's very important to practice. So I want to delete the 3 from the 3 you got. So let's say we have this. I deleted 3 here. So what can I replace with? I can replace it with 2 or with 4. Why not 6? Not the rightmost one. The leftmost on my right. So this is the leftmost. Okay, or the in order. If this is confusing for you, just do the in order and then you'll be able to choose it. So now we're going to finish from this and go to the Rook lab. Again, do you see, guys? O of H. O of H time. The height H is O of N in the worst case, O of log N in the best case. So the worst case, again, can be O of N, but the most accurate thing to say is O of H. Now we're going to cover the balanced next time. So let's go to the, so again, I left these for you to practice on it, guys. And let's go to the book lab. So that's where I usually either go home happy or go to the hospital because of the heart attack that you're going to give me. Take this.
Yeah.
So we have only 6 minutes, guys. Let's just do this fast. Okay, let's start. We can have same keys in a map. In a map ADT, can we have the same keys? False, false. Only in the priority queue we can have. Or we said there's something called dictionary ADT. That's different. Choose the right answer, or answers difference between maps and priority queue ADT is what? In a priority queue, we can have same key, while in maps we can't. In maps, I can delete whichever cell I want, while in priority queue, I can only delete the minimum or the maximum. That means here, the minimum and the max is the priority number. Both of them, of course. In this case here, in the maps, I can delete whichever cell I want, correct? If you didn't choose this because you saw here minimum and not priority, you're good. Implementing a map with unordered sequence using linked list. What's going to happen? For search, the worst case for is going to be O of n. But what about delete and put? We're using a linked list, unordered sequence. Delete and put. O of n. Why? Because linked list, technically it's O of 1. But we said we have to find the key first. We have to find it. Because if I want to delete or put, I need to find it. And if I want to put, it's O of 1 usually, but because it's a unique key, I need to check if the key exists before I do it. Implementing a map with ordered sequence. Now, ordered sequence using sorted array. For the array, we know that remove and insert can be O of n. What about searching?
Sticker.
We know that remove and insert is O of n because if I remove something, I need to what? Move everything in order. O of log n if I use binary search. If I don't use binary search, it's O of n. So it can be O of log n. Can I perform binary search on a sorted sequence implemented by linked structure, not array? Can I do a binary search on that?
Talk about tree.
Can I do a binary search on an ordered sequence, but it's implemented by linked list, not an array?
Not really captain.
To be or not to be? Correct? So yes and no. So this is not like a trick question, but it's a philosophical question. Technically, I can. It will not cost me log of n, but that's the problem. But I can do, like I will say, okay, I need to find the middle. I have to traverse each time. So it's going to be very bad, but technically I can. So
Yes.
which structure is better to use for map ADT implementation? Unordered, ordered, or search tree? I want to implement this ADT and make it a data structure. Search tree, yeah. So AVL 243s, red, black, these all of these are called search. But we only cover AVL and 243 in this course. But in the book, you'll find the other ones. Sorry? A binary search tree? Yes. 243 is not binary. That's why we're saying here search trees, because 243 is not binary. So search tree is a wider term.
Yeah.
Search tree, of course, guys. So let's go faster. Choose all right answers. Binary search tree characteristics are what? Each internal node stores a key and an element. Each internal node stores only a key. Key on the left child need to be smaller than key on of the parent. Keys on the left subtree need to be smaller than the key of the node. Very good. How can we traverse? By the way, here, guys, each internal node stores only a key. No, we said it's always key and a value. The key is to access, and then the value is the actual data. How can we traverse a binary search tree so that we visit elements and what in increasing order? Increasing. Reorder is visit left, right. So that means the root always need to be the first one. So we're going to exclude it. What about in order and post order?
Yeah.
In order. What is the cost of a successful search of an unbalanced tree? That means the worst tree. What is the cost of a successful search?
No. Straight line. I think.
Exactly. We already proved it. It's in the slides if you don't remember. Okay. What is the cost of unsuccessful search of an unbalanced tree? Unbalanced tree, it can be what? SQ tree. Unsuccessful. Of course, unsuccessful. I'm not going to find it anyway, so you're going to always take me off N, of course.
Case at least.
What is the cost of a successful search of a balanced tree? Now we're talking about balanced tree. Balanced tree can be perfect, complete, or just a balanced tree. So that means what?
Because it's not complete. We don't know whether.
Here, we're talking about balanced tree.
The tree is completely not.
Both are the same thing, guys. Balanced tree. In a balanced tree, the height is always log of n. That's the whole idea. That's why we're even having this lecture, right?
That's how you lose marking multiple choice. See the first answer.
And that's it. So good luck in your exams. Enjoy your reading week, and then we'll see you after the reading week.